Okay, so we're given the following function and the following domain, and we want to answer the following questions. The first thing we need to do is to calculate the function at various values of x. So let's start with f at -2 by just putting a -2 wherever we see an x. Okay, so f at -2 is equal to -9. Okay, now let's try f at -1/3. Now you have to make sure that you put these negative values in parentheses when you're raising them to an exponent. Negative kind of blended with the fraction bar there. So 1/3 plus 1. Okay. So to square a fraction, you just square the numerator and square the denominator. To cube a fraction, you just cube the numerator, cube the denominator. So okay, the least common denominator between these three fractions is 27. So I need to rewrite these. Okay. So that is equal to 32 over 27. And that's f at -1/3. Okay. Let's try the next one. F at 1. Well, that's just equal to 0. Okay. And the very last one is f 2 cubed, 2 squared, minus 2 plus 1. So it's 8 minus 4 minus 2 plus 1, which is equal to 3. Okay. Okay, so now we want to show that the function can be rewritten in this form. Now, because the function has 4 terms, it can be factored by grouping, which essentially means you factor the greatest common factor of the first 2 terms, which is x squared, leaving me with an x minus 1. Then you factor out the greatest common factor of the second 2 terms. Well, in this instance, they don't appear to have a greatest common factor other than 1. However, when we factor it out, what we're left in the parentheses needs to match this exactly. So if I factor out a 1, that won't work. But if I factor out a -1, that'll leave me with x minus 1 in my parentheses. The reason I needed that to be the same is because since each of these pieces here have this x minus 1 in them, I can factor that out, leaving me with x squared minus 1. Well, now this still doesn't match this expression up here. And that's because this right here is a difference of 2 squares. So I can now factor that as x minus 1 times x plus 1. And you can see that I have this x minus 1 twice, so I can rewrite that as x minus 1 squared times x plus 1. Okay. Now the only thing left to do is to find the zeros of the function, and because we have it in this factored form, it's actually pretty easy. All I need to do is use the zero product principle. So this equals 0 when x minus 1 squared times x plus 1 equals 0 when x minus 1 equals 0 and x plus 1 equals 0. And I didn't really need parentheses around this one, sorry. Okay, so that means x is equal to 1 and x is equal to negative 1. Well, or I should say. Okay, so the two zeros are 1 and negative 1. Okay, so I want to find the first and second derivative of this function, and then I want to determine when it is increasing and decreasing. So to find the first derivative, because this is a polynomial, it's not too difficult. I just drop down the exponent and then decrease it by 1. Okay. To find the second derivative, I just take the derivative of the first derivative. So I drop down the 2, multiply it by the 3, giving me 6x, and then minus 2. Okay, so I want to determine when it is increasing and decreasing. And I need to do that by setting f prime of x equal to 0. So f prime of x equals 0 when? Okay. Because what I'm looking for are the various critical values of the function. Okay, and you use the second derivative to find that. So I just have 3x squared minus 2x minus 1. Okay. So to solve this, the easiest way to solve this is by factoring. Okay. Now, this is a trinomial, so what I'm looking for are two numbers that multiply to give me negative 1 times 3, or negative 3, and add to give me negative 2. Well, in this case, it's negative 1 and, it's negative 3 and 1. So what I'm going to do is rewrite the middle term using those two values. Well, I don't need the 1, sorry. Plus x minus 1 equals 0. Now that I have four terms, I'm going to factor this by grouping. So I have 3x, and that leaves me with an x minus 1. And these don't appear to have a greatest common factor, which means the greatest common factor is 1. So if I factor that out, notice I have in each of these pieces an x minus 1, so I can factor that out. So this is known as the AC method for factoring a trinomial. Okay, so now what I can do is I can take these two factors and I can set them equal to 0 using the zero product principle. So this tells me x equals 1, and this tells me that x is equal to negative 1/3. Okay, so these are our critical values. So what we need to do is take those and then the endpoints of our domain and put them on an analysis line. So remember, the domain of the function is from negative 2 to 2. So we're going to start with those, negative 2 and 2. And since both of these values are in our domain, I'm going to write them on there as well. So this isn't drawn to scale, it's just relative position. That's all that really matters. Okay, so these are the values for x. I want to write what f prime of x is doing, and that'll tell me what f of x is doing. Okay, so what I'm going to look for is values within these intervals here, and determine if they're positive or negative. If they're positive, determine if the first derivative is positive or negative. Now, if it's positive, that means the function is increasing, and if it's negative, that means the function is decreasing. Okay, so let's just try them. So a nice value in between here would be, let's see, negative 1. Well, yeah. So f prime at negative 1, let's just use, remember the function is 3x squared minus 2x minus 1, so 3 times negative 1 squared minus 2 times negative 1 minus 1 equals 3 times 1 plus 2 minus 1, so it's equal to 4. Now, it doesn't really matter what the number is, all that really matters is that it's positive, so that means within this interval the first derivative is positive, okay, which means the function is increasing. Okay, so now let's try it at a value within this interval. The easiest one would be 0. So it's 3 times 0 squared minus 2 times 0 minus 1, which is just negative 1. Notice this time it is negative, so that means the function is decreasing. Okay, let's do one within here. This is the last one we need to do. This one we don't have a nice integer value, so we'll just use 1.5, f prime at 1.5. So that's equal to 3 times 1.5 squared minus 2 times 1.5 minus 1. So that's 3 times 2.25 minus 3 minus 1. So 6.75 minus 3 minus 1, or 2.75. Okay, so this one is positive, which means the function is increasing. Okay, so it is increasing on the intervals negative 2 to 1/3 and 1 to 2, so we represent that by using a union. Okay, and it's decreasing on the interval negative 1/3 to 1. Okay, so the next thing we want to do is find the extreme values and determine whether they are global or local extrema. And then we want to calculate the corresponding extreme values. So we've already actually done all the work for this. We used the analysis line that we used in part C and the evaluation of the function that we found at part A. Okay, so we use the thing that we found in part A to determine the absolute or global extrema. Okay, well notice that when we evaluate the original function at negative 2, we get negative 9, and that is the smallest one. So this is the global min. Okay, and when it asks for the corresponding extreme value, this is it. It's just negative 2, x equals negative 2, and y equals negative 9. Or f at negative 2 equals negative 9. And we can see that 3 is the largest one, so this is the global max. So this, you could say at x equals negative 2, at x equals 2. Okay, so at the endpoints of the domain. Okay, now the next thing to find is determine, okay, if these are global maxes, local maxes or local mins or nothing. But notice how it goes up and then it goes down, which means there's a peak here. So it is a max, but it is not the largest one because it's at 32/27, so this would be a local max. Okay, now because at x equals 1, it goes down and then goes back up. That's a valley, so it decreases and then goes back up. So this will be the lowest point in that range there. So this will be a local min. Okay, so the next thing we want to do is find the point of inflection and determine where the graph is concave up and concave down. Well, to determine these two things, you need to use the second derivative. The second derivative, if it is positive, that means the function is concave up, and if it's negative, that means the function is concave down. Now, if the function changes concavity at any place, that place will be called the point of inflection. So the first thing we need to do is determine when this second derivative equals 0. I just said, well, 6x minus 2 equals 0. So 6x equals 2. So x is equal to 2/6, which is equal to 1/3. Okay? So the next thing we're going to do is use an analysis line similar to the one that we did when we were finding when the function was increasing and decreasing. But this time, instead of using the first derivative, we're going to use the second derivative. Okay. Now we have to put our endpoints of the domain. Okay. And we also need to put this value here when the second derivative is equal to 0. Okay. Now you should also put when the second derivative is undefined, but since this is just a polynomial, it's defined for all values of x. Okay. So the first thing we need to do is determine when this is positive and negative within these intervals. So let's just put some various values in here. Okay, so let's try a value within this interval. Let's try f double prime at 0. So that's 6 times 0 minus 2, so that's equal to negative 2. Well, that's negative, so that means that the function is concave down. Let's try it for 1 in this interval, so let's try 1. So that's 6 times 1 minus 2, so it's 4. It's positive, so the second derivative is positive in this interval, which means the original function is concave up. Now the point of inflection is where the value, where the function changes concavity. So notice it goes from negative, downward concavity to upward concavity. So this is a point of inflection. So x equals 1/3 is a point of inflection. Okay. Now you probably will need to find the y value that goes along with this x value, and you do that by plugging it into the original function. Okay, let me double check, make sure that's right. Yes, that's the original function. Okay, now when you evaluate all of this, you'll get 16 over 27. So if you want to represent this point as an ordered pair, it would be 1/3 16 over 27. Okay. I forgot to write the concavity in interval notation, so it is concave down on the interval -2 to 1/3, and concave up on the interval 1/3 to 2. Okay, now these are intervals here, and this is an ordered pair. Okay. Okay, so I've just rewritten here some of the information that we got from previous problems. We found the function evaluated at these various points, and we said this was an absolute min, local max, so forth. And these are our analysis lines for the first derivative and the second derivative. So now we want to use those to graph our function. Okay, so remember we know that it is only going from -2 to +2. Okay, so what we're going to do is plot each of these points first. So it's at -2, -9. Okay, then at -1/3, 32 over 27, so that would be about here. Oops. It does say sketch, so it doesn't have to be precise. Okay, then 1/3, which is about right here, 1627, it's about right here. Okay, then 1, 0, that one's a lot easier to graph, and then 2, 3. Okay, and now you can see that, yeah, the 2, 3 is definitely the highest point, and -2, 9 is definitely the lowest point. So we were right when we said those were the absolute max and min. Now, what this says is that it is going to, from this point, from -2 to -1/3, it's going to increase, and it's going to have to be able to get there, but it's also going to be concave up from -2 to 1/3. Okay, so we need to make sure, oops, this is going to be pretty badly drawn because that doesn't look like a function. This is about as straight as I can, as good as I can get that. So notice it is concave down. Cool. And it's increasing. Now also after negative 1/3 it decreased. Okay, but it's still concave down. Now this is a point of inflection, so it needs to change concavity, so now I need to change it up. Okay, so this was my absolute or global max. This is my absolute min. This is, notice, it's the highest point within this area here, so this is a local max. This is my local min, because it is the lowest point within that area there, and this is a point of inflection, because it changes concavity there.